that pretty much ends the carbonyl chemistry unit, which you're probably glad to see go. And the next thing we're going to do is move into talking about conjugated systems and extended pi systems. So chapter 14 is extended pi systems that don't involve a ring, and then chapters 15 and 16 are aromatic. And we'll pick up a bunch of things from chapter 25, which is also on aromatics, heterocyclic aromatics, and some of 22, which is about phenols, which is aromatics that have an OH group on it. But before that, we're going to do the last of the types, sorry, the second to last of the types of spectroscopy. We talked about IR and NMR spectroscopy last semester. This semester we're going to talk about mass spectrometry, and we're going to talk about UV visible spectroscopy. And this becomes particularly relevant because there's a lab coming up for some of you this week that requires you to actually interpret the fragmentation pattern of the mass spectrum. And I'll have to do this lecture again for my lab section tomorrow because I don't think Dr. Cummins is getting to mass spectrometry yet. So if you're in my lab section, you'll probably hear a lot of this. So the question is, what is mass spectrometry, right? How does it work? What happens? The instrument we have is a little bit different from the one I'll be describing today. It's cheaper, and it uses a different type of mass selective detector, but the principle is kind of the same. And I'm going to use as my initial example just a simple alcohol. I'll just use 3-pentyl. Got a lone pair on the oxygen. So what happens is we put this in a chamber under high vacuum, and we have gold filaments. On either side of that chamber. And when I'm talking about high vacuum here, I'm talking about probably like 10 to the minus 5 pascals kind of pressure. So not just a rotary vacuum pump, we have a turbomolecular pump that really makes this a very high vacuum system. So there are not a lot of molecules in there that aren't 3-pentyl. And the helium carrier gas, but the helium carrier gas is going to be largely unaffected by what we're talking about here. So we keep these at a potential difference of around 70 electron volts, which is a pretty large potential difference. Electrons will build up on the negatively charged filament, and eventually, because this potential difference is so large, the electrons will build up enough on this filament that they're going to go shooting across. Okay? So we have an electron which is on its way from the negative filament to the gold filament. Most of the time, it will just shoot across. Sometimes that electron is going to run into an electron that's part of the molecule. And what happens when it does that is both the original electron and the electron it hits are going to get knocked out. It's going to impart enough energy to this other electron that both of those, that it will remove that electron completely. And what you'll do when that happens, you will create a charged species that has both an unpaired electron and a positive charge, or a radical cation. Right? This is now going to be swept. The radical cation is going to be swept by this carrier gas or by a magnetic field. It's going to be moved out of this little vacuum chamber. The vacuum chamber is over here, this cable. Right? It's going to be moved out of that vacuum chamber, and it's going to be focused by some additional plates with charge on them. So it will be repelled by the positive plate and attracted to the negative plate. And there'll be a detector over here. And if it's got just the right charge over mass or mass over charge ratio, it'll make it through and not crash into something. So we can vary the current on these things. To select for different mass of charges. If the mass over charge ratio, if the thing is too heavy, right, if the M over Z is too high, it will have too much momentum and it will not actually be repelled strongly enough by that positive plate, and it'll go crashing into the positively charged plate. Because the force of the attraction, or the force of the moving particle is larger than the force exerted by the positively charged plate. If the M over Z is too small, it will be pushed on by that positively charged plate so hard that it will not have enough momentum to make it all the way through, and it'll come down here and crash into the negatively charged plate. Only if the mass over charge ratio is just right will the balance of forces between the momentum caused by the mass and the electrostatic repulsion caused by the positive plate be just the right amount to allow it to make this curve path. Our detector is actually what we call a quadrupole detector. And what our detector consists of is a series of rods, metal rods. The particle goes through the center. We rapidly change from plus here to plus there, and your particle will actually go through. If it's too massive, it's going to have too much momentum and it's going to go crashing into one of these rods. And if it's got too little, right, it'll be repelled too hard and crash into the other rod. So we rapidly switch the polarity. What we're trying to do is we're trying to get that particle to stay in that little cylinder between the rods. We rapidly switch the polarity, we'll get that thing to kind of follow a helical path through, and then make it out at the end if it has the right M over Z ratio. And hit our detector over there. The quadrupole detector that we have is accurate to around plus or minus 0.6 atomic mass units. The cost of a GC mass spec with a quadrupole detector is somewhere around $75,000. The cost of one of these is accurate to plus or minus 0.0001 atomic mass units is about $500,000 to $600,000. So we obviously don't have a $500,000 mass spec that allows us to get this level of accuracy. At this level of accuracy, the difference between nitrogen, which has an atomic mass of 14, and a CH2 group, which also has a mass of 14, is different. You can actually tell the difference between nitrogen and CH2 with this high resolution mass spectrometry. You can't here. We can get a rough guide of the actual molecular weight of the compound, but we can't get enough information to get the full molecular formula. The purpose of mass spectrometry, one of the purposes, is to get the mass of the compound. Most of the molecules we're going to be working with are small enough that they only get one positive charge imparted to them, which means that this M over the M over Z ratio is actually the molecular mass. Right? That's only true if it's a +1 charge. If it's any other charge, then it won't. Right? If you have a +2 charge on here, you're going to see a peak at half the molecular weight compound, because there's going to be a lot more repulsive force from those plates, and you're going to need a different curve to get it to go through. For things like proteins and nucleic acids and large biomolecules, it's actually pretty common to have multiple positive charges on here, where several electrons will do this and put positive charge in different places of the molecule, and that makes interpretation a lot more difficult. But for simple organic molecules like we're working with, we're always going to assume that we only have one positive charge on the molecule, so So our molecular ion will give us the actual molecular mass of the compound. So this P here, this radical cation, is referred to as the molecular ion, and given the abbreviation capital M plus. Usually, it's the highest molecular weight on your spectrum. So what we're going to do is we're going to get a spectrum of intensity versus molecular weight, and up here, we're going to see our molecular ion. So what will the mass of that molecular ion be, assuming it's charged plus 1? The ability to do mental arithmetic, multiplication and addition, is really important for mass spectrum. So we need to know the molecular formula, C5H. Anybody? 12?
12, yeah.
Oh. So it's C5H12O plus, right? So we're going to see it. We only see ions that have positive charges. We don't see anything that's neutral. So it's C5H12O, either 60 plus 12 plus 16. And the important thing about mass spectrometry is you're actually seeing the individual molecule. So you're not seeing the weighted average atomic mass. You're actually seeing carbon 12, which is 12.000 atomic mass units. And you're seeing protein, right, the hydrogen plus. And you're seeing oxygen 16, not oxygen 17 and 18. So it's good enough to just use 12 for carbon and 1 for hydrogen and 16 for oxygen. You don't need any decimal places. So that's 88, right? So we're going to see a peak at M plus at 88 atomic mass units. We'll probably also see a small M plus 1 peak. Due to the natural abundance of the heavy isotope of carbon-13 that has that extra neutron, 7 neutrons instead of 6. The M plus 1 peak will get bigger the more carbons. Because carbon-13 has a natural abundance of about 1%, if you have a single carbon in your molecule, you would expect your M plus 1 peak to be about 1% of your M plus peak. If you have 10 carbons in your molecule, right, you'd expect your M plus 1 peak to increase because the likelihood of one of those 10 carbons being a carbon-13 increases. Pretty unlikely that more than one carbon is going to be a carbon-13. But if you get a large enough molecule, you do actually start to see an M plus 2 peak where you might have 2 carbon-13s in there. Deuterium has a really low natural abundance, so it's very unlikely you're going to see M plus 1 peak as a result of heavy hydrogen. But heavy carbon has a natural abundance that's large enough that that M plus 1 peak is there. And in the alcohol condensation lab, you have enough carbons in that molecule, you will actually probably see a significant M plus 1 peak. It's always less intense than the molecular ion though. This molecule number is stable, and it's going to start fragmenting. And so the pattern of ions that it fragments into, that's what's going to give us our distinctive ability to determine structure from mass spectrometry. So we have to know what kinds of things it's likely to do. How is that molecule likely to fragment in order to predict what that pattern should look like? But we also have a very large library from the National Institute of Standards that we can compare our mass spectrum to, and it's very much like a fingerprint. If you watch CSI or NCIS or any of the crime shows, you know that a GC mass spec is one of the main pieces of equipment that tells you who did it. And it doesn't really tell you who did it like it does in the shows. But the GC mass spec is really good at identifying compounds, especially if the compounds are in the library. So you can tell the difference between cocaine, heroin, and powdered sugar really quickly and easily with a GC mass spec. You can tell the difference between oregano marijuana really quickly using the PC mass spec. So if you're buying these things on the, at TV or something, you can bring them into the lab and check and make sure they're actually selling a good product. Okay. Easy to memorize a product like that. So we have our radical cation. It's going to fall apart. There are two primary ways by which these things fall apart. The first is through a process called alpha cleavage. This name actually comes from carbonyl compounds. If you have a carbonyl compound, and you make a radical cation here, for example, it is very common for it to fragment here between the carbonyl carbon and the alpha carbon, and that's where the name alpha cleavage comes from. Alpha cleavage is a homolytic bond cleavage. And that leads to a radical which is invisible because it's neutral, and a cation, and double cation, which is detected. So you don't see both fragments that come from alpha cleavage, you see just this one. And because the neutral particle is not seen. This is a terminal pathway. Once it's cleaved by alpha cleavage, it's not going to fragment further. The second pathway is a rearrangement. The rearrangement results in a new radical cation, which can fragment further. So you'll see the fragment, and then you'll see daughter fragments. We call them daughter fragments, I don't know why, that result from fragmentation of the first fragment. And a neutral molecule without unpaired electrons which is invisible to mass spec. So both of these generate one particle that's invisible on the mass spec because it's neutral, and one particle that you can see because it's still a carbocation. One of them is a terminal pathway. The other one has the ability to create additional fragments from the fragments. So the question is, when you're looking at a mass spec, how can you tell the difference between a fragment that resulted from alpha cleavage and a fragment that resulted from a rearrangement? And the answer is, if it results from an alpha cleavage from an even numbered molecular ion, you're going to see an odd numbered fragment. If, on the other hand, it's a rearrangement, I'm going to abbreviate RAR, rearrangement, an even numbered, and plus are even. And if it's an odd numbered molecular ion, the alpha cleavage will give you odd numbered, and the rearrangement will give you even numbered. Basically, the alpha cleavage process switches it. Whether you were even or odd, it's the other one and the rearrangement results in the same, even or oddness.
Do you mean like where the peak is at? Yeah,
Yeah,
that's
okay.
what you mean by even and odd?
88 is an even number. Processes that result from alpha cleavage are going to have odd numbered MO-proceeds.
Okay.
They're going to be less than 88, right? All of the
Yeah.
fragmentation peaks are going to be less than 88, but it's also going to be an odd numbered fragment. If it comes from a rearrangement, it's going to spit out a molecule that has an even numbered mass, and it's going to give an even numbered fragment. So when you're looking at the mass spectrum, you can tell where it came from. And that will tell you which ones could fragment further and which ones can't, right? Because the alpha cleavage pathways can't fragment further. Mass spec, by the way, is a total bitch, because these things fragment in all kinds of weird-ass ways, and you get peaks everywhere. And figuring out what the molecular formula of those peaks is quite challenging in many cases. There are some fragmentations that are common enough that we can actually use them, and then there are some fragmentations that are obscure, and sometimes you can't really tell. Just like the IR, right? Some peaks we can identify what bond they came from, and we know carbonyl is at 1700. Some peaks are just there, because there's a bending mode that absorbs that, but you can't actually tie it to an individual peak, but it does create a really nice fingerprint that will allow us to search the wavelengths. So the question is, how might this fragment, both by alpha cleavage and by rearrangement? So let's look at alpha cleavage possible first. What we're trying to do is we're trying to fragment it in such a way, or it is trying to fragment in such a way that it generates cations and radicals that are pretty stable. So one way that you could fragment this, and generate a pretty stable carbocation, right? We'd like to have something that's resonance stabilized, is to break this bond here, take one of the electrons and combine it with a single electron on oxygen, and create a pethyl radical. This is a resonance stabilized cation. So that's going to be a pretty stable cation. That's the peak we're going to detect. This is a loss of C2H5 radical. And C2H5 has a molecular mass of 29 atomic mass units. So what we're going to see here is an M-29 peak. So instead of a peak at 88, we're going to have a peak at 88 minus 29. It's usually easier to determine the mass of what's lost than it is to determine the mass of what's kept. Right? So you're going to look for distinctive peaks at loss of methyl, for example. So M minus 15 is usually loss of CH3. M minus 29 is loss of ethyl. M minus 43 is loss of propyl. And M minus 57 is loss of butyl. So when you see peaks that are 15, 29, 43, or 57 or less, those are usually alpha cleavages. Or that the bond breaking and forming methyl radical or ethyl radical or propyl radical or butyl radical. In this case, there's two different bonds that could cleave with loss of C2H5 radical. That's probably going to be a pretty good pathway. So we're going to see a fairly large peak at M minus 29. So what is M minus 29 from a molecular weight of 88? Take away 30 and add 1. I didn't hear you.
Oh, I said 59.
59. Because there's two different ways for it to do that, that may well be the most intense peak. And the most intense peak is called the base peak. And the base peak is arbitrarily set to 100%. And then all the other pieces scale to that. So what you see when you see the mass spectrum is you'll see the total ion count. The total ion count might be 3.5 million, right? Because there's lots of these molecules going through the system, and they're all being fragmented the same way, and they're all crashing into the detector. So you might actually see 3.5 million individual ions. If it's the base peak, we're going to divide through by 3.5 million, multiply by 100, and just call that 100%. And then we will scale the total ion count to a percentage. So that's a pretty, yeah, is there a question?
Can you explain how you got to 59?
Yeah, I took 88 and I subtracted the 29.
Oh, okay, thank you so much.
7 minus 2 is 5. So this peak is gone. 29 atomic masses and 2 carbons and 5 hydrogens have been spit out in an invisible fragment, and what we're left with is the remainder. You could also do this by noticing this is C3H7O. So that's 36 plus 7 plus 16. If I didn't fuck up, that should add up to 59. But as I said, it's usually easier to use your molecular item and subtract what disappeared than it is to constantly be figuring out the molecular weight of the actual fragment. Does that cover it? Answer your question?
Yes, thank you.
So we should see a pretty significant peak at 59 because this is a nice residence stabilized carbocation. There's 2 different ways it could be generated. How else might it fragment by alpha fragmentation? It's not really likely to lose a methyl group. So we're probably not going to see a big peak at n-15 because a radical here and a radical here would have to combine into a 3-membered ring in order to form a stable peak. It might. Right? It's possible. If we do see an n-15 peak, we can certainly explain why by cleaving this bond, spitting out CH3 radical, and generating a cation that looks like this. That would be an m-15 peak. So where would that be? 73. Notice that both 73 and 59 are odd numbers. Odd numbered fragments from alpha cleavage. But this cation isn't nearly as stable as this cation. So it's much less likely. You would think that an m-29 peak should be more prominent than an m-15 peak. There is no good way for it to lose a propyl group. So you shouldn't see an m-43 peak at all, right? There's no alpha cleavage that's going to kick out C3H7 from that molecule. There is another good fragmentation, though, that could generate a resonance stabilized cation through an alpha cleavage. And that's instead of breaking the bond with carbon, you might break the bond with a hydrogen. So if we broke this bond, we can spit out a hydrogen radical and a resonance stabilized carbocation that looks like that. And that would be m-1. It is almost always possible for a molecule to fragment in some way by losing a hydrogen radical. So it's pretty common to see an m-1 peak. Sometimes the N-1 peak is actually bigger than the M peak. Right? So your molecular ion peak will be small relative to your N-1 peak because there are so many different ways you can lose a hydrogen radical to form a stable carbocation. And so you don't see the molecular ion very strongly. Sometimes the fragmentation is so fast that you don't see the molecular ion at all. And that's really freaking annoying because you're looking for that highest molecular weight peak to be your molecular weight of your compound, and that peak's invisible, and all you're seeing is fragmentation. T-butanol is an example. The radical cation from tertiary butanol, which is one of the products from the Morphling lab that you're working with, so readily loses the methyl group. And there's three different ways it can lose the methyl group. It forms CH3 and the resonance stabilized carbocation that has the other two groups on it. But you don't actually see this. All you see is that. All right, so the M plus is invisible. Too small to detect. And you'll actually see that because I took the mass spec of this product from the Morphling lab, and that mass spec is available to you. So what's the molecular ion for T-butanol? C4, H10O, because it's saturated, right? So CnH2n plus 2.
38.
48 plus
48.
10 plus 16.
Oh, I just did one carbon.
It's got 4.
Yeah, never mind.
74?
Oh, gosh.
But you're not going to see a 74 peak. You're going to see an M minus 15 at 59. And that's going to be your base peak. So anytime you have an alcohol, it is common to cleave between the carbon that's attached to the oxygen and the next one, which would be considered the alpha carbon, right? So this is the carbon that's actually attached, that's the alpha carbon, and that's why it's called an alpha cleavage. It's annoying when your molecular ion is not visible, but sometimes you can explain readily why it's not visible, just because the fragmentation is so rapid. So for this molecule, this M over Z88, we'd expect to see some at 87, right? But the hydrogen radical is not that stable. We'd expect to see quite a lot of 59 for loss of the ethyl group. We really don't expect to see a lot of N minus 15. We shouldn't see any of this because there's no good fragmentation pathway with which we need to those. So what about rearrangements? What kind of rearrangements do molecules do? And what usually happens in a rearrangement is the radical cation, wherever that radical is it plucks a hydrogen off somewhere else in the molecule to spit out that neutral molecule. A very common rearrangement for alcohols is to lose water. And they give an M minus 18. Because duo has a formula mass of 18. So you have this radical cation. We have adjacent hydrogens. So what's usually going to happen is it's going to pluck one of those hydrogens off, turning a radical here, and it's going to take those two with it. The result of that will be to form a molecule that looks like this. That's a radical cation. Right? So this lone pair is here. This lone pair used to be this bond to carbon. This radical has now formed a bond to that hydrogen, that's this bond, and left one behind. This is a pi bond with one electron in it. You could also write a resonance structure that has a radical on this carbon, positive charge on that carbon. Lewis structures don't really do a very good job of expressing what that looks like. It's really just a bonding pi orbital, but a bonding pi orbital is only half filled. So you have a pi bond order of 0.5. So this is 18. This is going to be M minus 18, which coming from 88, right, the molecular atom of 88, means you see a peak at 70. It's an even number. It came from an even number, so you would know that that peak at 70 came from a rearrangement rather than an alteration. Loss of water is the most common rearrangement that you're going to see for alcohols when they fragment. This is subject to further rearrangement, though. If we can cleave that in such a way to generate something that's resonance stabilized, we might see that effect. And I think you can see that from this resonance form. If we were to cleave this bond and take out methyl group, the other product would look like this. Take one electron from that carbon-carbon bond to the CH3, form a pi bond here, and this is a little bit resonance stabilized. We can have two resonance contributors. This is the major resonance contributor because positive charge is on the more substituted carbon, as opposed to the minor one where it's on the less substituted. But again, a resonance stabilized carbocation, when the carbocation is adjacent to a pi bond, should be fairly stable. And methyl radical can fly off because there's very high energy species. Right? 70 electron volts is a lot of energy. So when you look in the mass spec in the literature, what you'll usually see is you'll see them saying MS PI 70 electron volts. PI stands for electron impact. Which means you're firing electrons at an energy of 70 electron volts and using that to kick other electrons out of orbit. So EI, electron impact of 70 electron volts, that's a fairly standard technique. It works really well for relatively insensitive molecules. For big molecules like proteins, the electron impact is not really a very good way. So there are lots of other types of mass spec that you'll see. There's CI, which stands for chemical ionization. There's FAD, which stands for fast atom bombardment. There's MALDI, which stands for matrix-assisted laser desorption ionization. There's electrospray ionization. There's lots of different ways of generating these radical carbocations that are kind of targeted to an individual type of molecule. Electrospray ionization is very common, for example, in liquid chromatography, mass spectrometry, where you're using the HPLC column first and then running it. MALDI combined with a TOF, time of flight detector, is really good for big things like proteins and nucleotides and polymers. Right? But all the small molecules, usually you'll see an EI, electron impact of 70 electron volts. So where would this fragment be? Where would we expect to see that?
Is it n minus 15 from the last one?
It's 70 minus 15. This
But then
is
that's
15.
an odd number.
Right, so the MOVC for this is 70 minus 15, 55. So we might expect to see, if we see a peak at 70, we might also expect to see a peak at 55. And it's an allylic resonance stabilized carbocation. It's possible that's actually the base peak. Maybe. I don't know what the spectrum is like. The loss of water happens pretty readily, and the fragment that results from loss of water can easily lose methyl to form a cation. So you'd expect to see a peak at 55. If you see a peak at 70, if you don't see the peak at 70, you're probably not going to see the peak at 55.
Okay,
Because
so
usually when you have n minus 18 and minus 15, right, so this is going to be n minus 18 minus 15. It's usually the 18 that comes off first, the rearrangement. If you lose a methyl group, that's an alpha cleavage, that's a carbocation, that's not subject to further rearrangement. So once you've lost the methyl group from your molecular right, you can't lose water from that.
okay, so it's only that kind of, when you're saying fragments from rearrangements, like of an even numbered mass would be even only for that first one.
Right, because this is an alpha cleavage process.
Right, okay,
And the
thank
alpha
you.
cleavage process changes the odd or evenness on the fragment. So the rearrangement is even, but then the alpha cleavage from that is back to being odd.
Okay,
So that's an example from an alcohol, right? There are lots of other kind of classes of molecules that fragment in some predictable ways. Before we talk about any of those, we're going to take a break. And before we take a little break, which we'll do in a few minutes, I want to talk about some other distinctive things that you can look for in the mass spec to give you useful information. And one of those is what elements are in the molecule. Besides C, H, and O, right? C, H, and O are pretty common in organic molecules. A lot of organic molecules have some of those. If there's an N and an odd number of them, then the molecular ion is odd, not even. So if instead of working with 3-pentanol, I work with 3-aminopentane, I bombarded this thing with electron impact at 70 electron volts. I would create the same thing. Usually the radical cation is when you create it either somewhere where there's a lone pair, one of those lone pair electrons is going to come off, or somewhere where there's a pi bond, where one of the pi electrons is going to come out. And that's because those are the highest energy electrons in the system. If it collides with an electron anywhere else in the system, it will take out a lower energy electron, and then the higher energy electron will fall back down. So what's the molecular formula here? Seven, right? So that's an odd molecular ion. Why is that odd? It's because when you put a nitrogen in there, the nitrogen has a valence of 5. It comes with 2 hydrogens rather than 1. Right? When it was an OH group, the oxygen just went in and kept the other hydrogen that it replaced. So the nitrogen adds an extra hydrogen. So an odd numbered molecular ion often tells you there's nitrogen in your molecule. If you have an even number of nitrogens, if you have 2 nitrogens in the molecule, then that goes out the window. It's actually even. But there are lots of organic molecules that contain a single nitrogen, and they will all have odd numbered molecular ions. The fragments for that from alpha cleavage will now be even numbered. So if you did the alpha cleavage here, like the same way that we did for the alcohol, you're going to get the C2H5 radical. 29, and then you're going to get this. This radical 1 residue structure this time. That's going to be an M minus 29. Now, instead of being at 59, it's going to be 58. Oh,
Yeah.
this is C3H. 8. And that's going to be 58, right? So the odd or evenness changes when you know. You could also lose ammonia, right? Ammonia would be a rearrangement that you might expect this to be able to go. And if you lost ammonia, you would get that same radical cation with a single electron in it that we got from the fragmentation from the pentanol. And you would expect to see this in the same place. 7. Yes? And then that fragment to give the 55. So you might expect 3-pentanol and 3-aminopentane to give the same 70 and 55 peaks that 3-pentanol would give, right? But instead of having 59 peak, you have a 58. And your molecular item, instead of 88, you see 87. So you can tell the difference between those by mass spec. So that's nitrogen. The other places where it becomes really useful to look in the molecular ion region is when you have 2 isotopes. So if there's chlorine, which has 2 common isotopes, 37 chlorine and 35 chlorine, the average atomic mass is 35.453, but no chlorine atom has a mass of 35.453 atomic mass units. They're either right around 35 or right around 37, and it's about a 3-to-1 ratio of natural abundance. And that leads to a predictable pattern where you have an M to M plus 2 ratio of 3-to-1. So you'll see a pattern that looks like this, where the intensity of the M plus 2 peak is about a third the intensity of the M plus 2. That's very distinctive for chlorine. You're looking at the M plus 2 peak. For bromine, you see an M plus to M plus 2 ratio of approximately 1-to-1, because the 2 abundant isotopes of bromine, 79 bromine and 81 bromine. Right? So if you look at the periodic table, bromine has an average atomic mass, or weighted average mass, of about 80. Right? But no bromine atom has an atomic mass of 80. They're either 79 or 81, and since the natural abundance is about equal, there's approximately a 50-50 chance that your molecule has a 79 bromine in it and an 81 bromine in it, so you're going to see a distinctive pattern where your M and M plus 2 look about the same height. If you have more than 1 bromine, right, you're also going to see a really distinctive pattern. Both of your bromines are 79, you'll see your molecular ion. If one of them is 79, the other one is 81, you'll have N plus 2. If they're both 81, you'll see N plus 4. What will that pattern look like if you have 2 bromines?
One, 2, 1.
So you got one possibility, 79, 79, another possibility, 79, 81.
Oh, it's a 1 to 3, 1.
Those are the 4 possible ways for those 2 bromines. This one's twice as likely. So you should see a 1 to 2 to 1 pattern. A 1 to 2 to 1 pattern in the molecular ion region, M to M plus 2 to M plus 4, really tells you there's probably 2 bromines in the molecule. Chlorine will do the same thing. The pattern will be a little bit more complicated because it's not a 1 to 1, it's a 3 to 1. But 2 chlorines will also give a distinctive pattern of M to M plus 2 to M plus 4. The other place where looking at the M plus 2 can help you is if there's a sulfur in the molecule. 34S is about 4% as abundant. That's 32S. So your M to M plus 2 ratio is approximately 4% the height of the atom cluster. So 4% probably sulfur, a third the height probably chlorine, the same height probably bromine. So you can tell if one of those elements is present. You can tell nitrogen is present if it's an odd number. If there's iodine present, you are going to see a peak at 1.7. Iodine is so large and polarizable that the iodine cation is actually pretty stable. So any molecule that contains iodine is going to fragment in such a way to generate I plus and a carbon radical. All right, that's a shit ton of information. Let's take a break. And then we'll fragment some more things. It didn't say I was going to spend the whole day on Mass Spec today. It said I was going to get into the Lilith systems, but I'm spending the whole day on Mass Spec because we need it. And then the quiz will be on Mass Spec. I'll give you molecules and ask you to fragment them and predict what's going to happen.
Oh boy.
Oh boy, it'll be fun.
Oh, nice.